So I will be talking about some results in complex geometry, but the method is from symplectic topology, but mostly fairly standard tools from symplectic topology. So let me start with a question, which is a compactification of Cn. So the setup is you have a pair X and D, and X is a smooth complex manifold, and D is closed analytic subspace. That means like locally it's cut out by holomorphic functions, such that the complement of this D is biholomorphic to Cn. That's what I mean by compactification of Cn. So let's look at some basic examples. For example, when n is 1, then you only have one compactification, which is a P1, and the D is a point. So I call it P0. And when n is 2, you still have this example, which is P2 and P1. But you have more. For example, you can consider Q2, which is a quadratic surface. So this is inside P3. And then this H is a hyperplane. And you require this hyperplane to intersect this quadratic surface at a tangent to a point. Then you can verify the complement is, again, biholomorphic to C2. So in fact, the pair here, this Q2 is diffeomorphic to S2 times S2. And this divisor is S2 times infinity union infinity times S2. And you do see the complement is just the C2. And this family of example will persist in all high dimensions. So in like high dimensions, you have this standard pair, which is Pn and Pn minus 1. You also have the quadratic hypersurface. Now it's in P4. And you choose a hyperplane, which is a tangent to this quadratic hypersurface. And in this case, Q3 intersects this H. This divisor will be a cone. It's a projective cone over a quadratic curve. The previous example can be viewed as a cone over 2 points. Okay. And we will call this Pn minus 1 is a standard compactification. And as you can see from this problem, there are more compactification than just a standard compactification. So the actual problem proposed by Herzberg is the following, because if you think about this problem is not like asking all the compactification of Cn is not like a finite problem, because you can always blow up a point or blow up a subvariety in D that will not change the complement. So we have to rule out that possibility. And the one way to do that is impose this condition of B2 of your compactification is 1. And this is equivalent to that D is irreducible. So in the previous slide, this example will be like take out. Because this divisor is reducible. But this example is good for the compactification problem, the Herzberg's compactification problem, because this divisor is irreducible. Okay, and yes, this is what I said. Sorry, I didn't say this yet, but when dimension is smaller, with this condition that D is irreducible, all the compactification is standard. And when n is 3, we also have a complete classification of all such compactification. The reason is you can show that X is always Fano. This is true for all dimensions. But we sort of have a better understanding of Fano manifold in dimension 3. So we can go to the list to see whether we can find a C3 in it. So this problem is solved in dimension 3 with this assumption that this X is projective. Because the original problem, we only assume that X is a complex manifold. And this also, Herzberg's original problem is only complex. Okay. So the moral standard is sort of similar to all the questions in all kinds of geometry, that classification is always very hard, especially when you go higher dimensions. It's often maybe hopeless. So maybe we can ask a weaker question, which is, can we characterize the simplest one, which is a standard compactification? So this line of studies started with the theorem of Brenton and Morrow quite a long time ago. They show that when n is 3 and D is smooth, here they do not assume this X is projective. Then this XD must be standard. So they propose that the condition that characterizes compactification being standard is precisely this D is a smooth submanifold. And in fact, they show that it actually suffices to prove that this D is biholomorphic to Pn-1. Okay. And in a survey paper by Peternow and Schneider in '89, they sort of survey the question of compactification of Cn, and they propose to solve this problem in 2 steps. The first one is solve the problem assuming X is projective. And this has been done when n is smaller than 5 by Van der Waals and n smaller than 6 by Fujita. And in the case of without assuming this projective, actually in the work of Brenton and Morrow, they actually show that all such compactification has to be projective. Then yes, so follow the line of this strategy of proving by 2 steps. The first one is the simpler one, that is you work under the additional assumption that X is projective. And our main result is this result is true. The first step is indeed true. That is the compactification must be standard, assuming X is Kähler and D is a smooth divisor. And shortly after we post the papers, there's a shorter proof by Peternow. But that's not true for all the cases, just for n is even. Yeah, so his approach is based on Riemann law. So more along the line of the classical study due to Van der Waals and Fujita. Yeah, okay. So next we can consider a slight generalization of the problem, which is we consider the orbifold analog. So now we consider X is a smooth orbifold or smooth complex orbifold or smooth Kähler orbifold, and D is a smooth suborbifold. So even though we have singularities, but as orbifold, it's a kind of smooth submanifold. And there are more examples of the compactification. So a typical example is this pair of weighted projective space. So this weighted projective space here is just Cn plus 1, delete a 0, quotient by a C star action. And the C star action on it is just given by this weight. Lambda to the W1, C1, and W and C. Where this Wi are positive integers. And you can verify if you delete this sort of a hyperplane at infinity, the complement, because the first weight is 1, the complement is biholomorphic to Cn. And we conjecture this is all the compactification if you consider XD are orbifold and D is a smooth suborbifold. And we want to remark here in this setup, it is important that the orbifold singularity of D is inherent from X. That is what we mean by a suborbifold. So the isotropy of a group of a point in D, it must be the same as the point, same as the isotropy of that point in X. So it's the singularity is not from D itself, but inherent from X. And the reason why it's important is if you take this example, then the divisor itself is actually, as a variety, is the same as a weighted projective space. So this justifies this condition. And when you look at this type of generalization, a natural question is, why do we care about orbifolds? One answer is because orbifolds are generalizations of manifolds. So we can, of course, think about that if we have a manifold version of the theorem. But there's actually a better reason why orbifold matters, a compactification matters here. So let me take a detour to the case with like the case of Riemannian geometry with metric. So let's first recall the definition of a Sasaki manifold. So a Sasaki manifold is a all-dimensional manifold with a metric and one form alpha. It's called Sasaki if the cone, which is here, is kind of the syncretization of this n with a cone metric. So this r is the coordinate on this r plus, and with a kind of a conical symplectic form built from this alpha, which will be a contact form. If this triple or this triple is a Kähler manifold, and that will also determine a complex structure, which will be sort of admissible in the sense of SFT, if you want. So the Sasaki manifold is sort of the Kähler analog of a contact manifold. And then we can talk about what do I mean by a Kähler manifold is asymptotically conical. So a complete Kähler manifold is called asymptotically conical, or shorted by AC, means the following is sort of the W at infinity, where it looks like this Sasaki cone. So you can find the asymptotic cone, which is this manifold with some Sasaki manifold n, such that there exists a compact set. After you delete a compact set K from W, the complement will be very close to this Sasaki cone. That is, you can find the diffeomorphism identifies these two domains, so that under this identification, the metric is close to each other and the complex structure is close to each other as R goes to infinity, as it approaches the end of this manifold. Actually, in the more precise definition, there's a kind of actual rate about how fast this will converge, but it does not matter very much in our talk. So in a slightly fancier language, this saying that a Kähler manifold is asymptotically conical if it has a tangent cone at infinity is modeled on this Sasaki manifold. Okay, and then since we talk about Sasaki manifold, it's actually a special case of contact manifold. So let me just quickly recall the definition of contact manifold, which is just an odd-dimensional manifold with a hyperplane distribution, and this hyperplane distribution is a kernel of one form, and this one form satisfies this condition. And that will determine as a Reeb vector field characterized by these two conditions. And the contact manifold are naturally boundary of Symplectic manifold. And in this talk, our mainly interest in the Liouville fillings or Liouville cobordisms. And here is a definition. Okay, so I guess these are probably very familiar to most of the audience. So I'll just go to the next slide. Okay, so let's return back to the Sasaki case. In this case, our contact structure is a complex tangency, which is sort of the part of the complex structure, so part of the tangent space of this Sasaki manifold with the complex structure. This J is a complex structure on the cone. Okay, and the contact form, of course, it's part of the Sasaki data, but you can also using the complex structure and this radius function to write it as this way. And we will call this, like all these Sasaki contact form as called the conic contact form. And the Reeb vector field, in the general case of a contact manifold, the Reeb vector field will preserve the contact form. But in the Sasaki case, it will preserve everything. It's a scaling vector field, so it preserves the metric, and it's also holomorphic on the synthesization. It's a holomorphic vector field. So in particular, it will generate a C star to the end, a torus action on the Kähler cone. So this is just you take sort of you sort of first you have just one direction of the axis vector field, but you can take a sort of the closure of this action to get a C star to the M action. A basic example is you consider this ellipsoid. And if all the AI and the standard contact form will give you a Sasaki structure on it, and if all the AI are rational, then the Reeb vector field is sort of all the Reeb orbits will be closed. So it actually generates a one C star to the one-dimensional torus action. But if we have some of AI are not rationally dependent, then it will actually generate a high-dimensional torus action. Okay. Yeah, and when we call that M equals to 1, it's called this contact form. It's quasi-regular. And when M is bigger, it's called irregular. Just their concept in Sasaki geometry. Okay, so the reason why we care about this Sasaki metric and the asymptotic conic metric is if your tangent cone at infinity, it has a Sasaki structure, then you can have orbifold compactification of the original Kähler manifold. So this is a theorem due to Li, my co-author from Rutgers, and also Helen and Conan and Helen. They show that so orbifold compactification will appear naturally in the compactification of domains with AC metric. And by natural, I mean it's sort of come up with all these nice estimates. And when m is 1, this compactification is simply adding this m quotient by the Reeb vector field. M is a Sasaki manifold. So in the case of this rational ellipsoid, this is indeed giving you the compactification of Cn into a weighted projective space. But if your if your Reeb vector field generates a higher dimensional torus action, then you have to perturb your Reeb vector, you perturb your contact form a little bit, because in this torus you can always find these rational directions are dense, so you can always perturb, and then use the perturbed Reeb flow to do the quotient and to compactify. But with this perturbation, this compactification, the estimate in the compactification will be slightly worse than for the regular case, which is m equals 1a case. So that's the reason why we care about orbifold compactification, because it's natural in the compactification of all these asymptotic conical metric. So the question is, why do we care about asymptotic conic metric? So this is related to a question in the study of this matrix on Tian, in particular the Calabi-Yau matrix on Tian. So there's an old conjecture by Tian, which says that any complete Calabi-Yau matrix on Cn with maximum volume growth must be flat. So maximum volume growth means that if you take a larger and larger ball inside this domain, the volume growth rate is the same as the growth rate of the on the Euclidean Cn. And this is maximum due to the Bishop-Gromov volume comparison. Unfortunately, so Tian proves this conjecture when n is 2. But unfortunately, this conjecture is not true when n is bigger or equal to 3. And the first counterexample is due to Yang Li. And he shows that there's a complete Calabi-Yau metric on C3 with a singular tangent cone at infinity. The tangent cone at infinity will be like this C2 quotient by Z2 times C with all the flat metrics on it. Yeah. And if we try to think of this using the language of this asymptotic conic metric, we can think of what is the Sasaki link here. We're trying to find the unit ball, unit sphere in it. But you will see that this quotient singularity Z2 will induce the S1 family of singularity on the link, on this Sasaki link. So in particular, you can view the example by Yang Li as sort of a asymptotically conic metric with a singular Sasaki link. And the higher dimensional, similar higher dimensionals are also found later. Okay. So first of all, the asymptotic cone metric is always having the maximum volume growth, because just by definition, the metric look more and more like a cone metric, and cone metric has volume growth as a Euclidean metric. And Liang's example is precisely asymptotic conical with a singular but codimension 1 link. So codimension 1 link will imply that the volume growth is maximum, but his link is singular. So we propose to fix Tian's conjecture, because it's a quite natural question to characterize the flat metric among all the Calabi-Yau metrics on Cn. Then we propose the condition here is this AC condition. So the claim is any complete AC Calabi-Yau metric on Cn must be flat. So the AC here is in the strong sense, the Sasaki link has to be smooth, because if it's singular, then you have Yang Li's counterexample. Okay, and our second theorem is saying that this conjecture is true, if another conjecture, maybe a harder conjecture, is true. Oh, Shortkanov conjecture. This conjecture about singularity I will recall in a minute. But I want to mention here that we do not require this conjecture holds for all the singularities. We only need to hold for a special class of singularity called the Fano singularity, which I will recall in a minute as well. But the good news is we know that Shortkanov conjecture holds in dimension 3 because more or less we can classify things. So in particular, we know the conjecture is true in dimension 3, which is good because that's the case where that's the dimension we have a counterexample if we lose this smooth condition on the Sasaki link. Okay, so the second part is we recall some basics about about algebraic geometry and to recall what's this Shortkanov conjecture and what we actually proved. So the setup is the following. Let X be a normal Q gross time variety and O is an isolated singularity. I'm not an algebraic geometer, so these are pretty much just words to me. But this basically means you can write down this formula, compare these divisors. Okay, so the situation is we consider resolution of your singularity O. And by resolution here, I always mean the resolution so that the exceptional divisor is simple normal crossing. And then we can compare the canonical divisor. Sorry, here should be x tilde. So I can compare the canonical divisor of the resolution with the pullback, and that will come with some discrepancy. And the discrepancy is purely supported in the exceptional divisor. So we can write out this relation about divisors. And the minimum discrepancy of the singularity is defined to be the minimum of AI, if the minimum of AI is bigger or equal to -1. And it's defined to be minus infinity if this AI is some AI, the minimum AI is smaller than -1. So if you have just find one resolution and you compute it, find it bigger than equal to -1, then it's actually independent of the resolution. But if you find some resolution, find some AI smaller than -1, you can keep doing blow up to make it smaller. That's why we define to be minus infinity. Okay, and the Shortkanov conjecture is a conjecture in the variational geometry. It's not the original statement of the conjecture, but this is a corollary of his conjecture, which says the minimum discrepancy of an isolated singularity will be smaller than complex dimension -1. And this is the minimum discrepancy of a smooth point. And when the equality holds, this O cannot be a singularity. And it is true up to dimension 3 and some special cases, for example, if your singularity is a complete intersection. Okay, and then I will give another definition of sort of understanding of this discrepancy from topology perspective, which is due to MacLean. It's the following. So given isolated singularity O, we can talk about the link of this singularity. So this link is, first, you can sort of embed this X into some big Cn, or just a neighborhood, part of neighborhood of this O. And then you intersect this X with a very small sphere that will give us this link of N. And from now on, I will not care about the topology of X or X tilde outside this neighborhood. So my X tilde is sort of a filling bounded by the link N. And this M is naturally a contact manifold with a contact structure is a CR structure, or it's a complex tangency. So it's the Tn intersects with JTn. And it's a contact morally because this R square on Cn is strongly pseudo-convex. It's a PSH. Okay. So it's always contact manifold. And the Q-Grosstein condition will imply that the first chain class of the rational first chain class of the contact structure is 0. Then, because of this, we can view the rational first chain class of the resolution, which is just the domain bounded by this M, as in the relative cohomology. But we know that this relative cohomology will be isomorphic through the Lefschetz duality to the space spanned by the fundamental class of EI. So we can write the first chain class as a linear combination of this Lefschetz dual, and you get the coefficient here is precisely AI. And this is the same AI as before. But this is just taking the first chain class of this relation near the singularity. Okay. So a simple example of a singularity is following. We can consider D be a Fano manifold. The Fano here just means the canonical divisor, this KD, is a positive, negative KD is a positive multiple of L, and L is ample. Okay. And then we can consider the following space, which is a spec of this algebra. And this space is just the space is the same thing as you consider this line bundle of L inverse over D, and then you contract the zero section D, and you get a singularity in the center. And you can vary using the definition that the minimum discrepancy here is precisely this R minus 1. So here comes our definition of Fano cone singularity. The Fano cone singularity is basically this, but we allow that D to be a Fano orbifold. So again, the space is again it's an orbifold line bundle L inverse over D, and you contract the zero section. And in the case of Fano orbifold or Fano manifold, the maximum index R is called the Fano index. That is, the maximum R such that you can find the ample line bundle L such that this holds is called the Fano index. And in Brenton and Morrow's conjecture, because they show that it's enough to they show that the conjecture reduced to D is biholomorphic to Tian minus 1. And there's a classical result due to Kobayashi-Ochai, which says if a Fano index of some n-1 dimensional manifold is n, that will imply that X is Tian minus 1. So the game is to compute the Fano index of the divisor at infinity, but the Fano index will be related to minimum discrepancy and first chain number, and then to symplectic geometry. That's morally what's going on here. Okay, so the actual main result we proved is the following theorem. It says if O is an isolated Fano cone singularity of dimension n, and for any quasi-regular conic contact form, that is the sort of Sasaki contact form, such that the Reeb vector flow will generate an S1 action, we have the following formula for the minimum discrepancy, which says twice the minimum discrepancy is the infimum of the SFT degree. Here, the infimum is a range over all the closed Reeb orbits of this contact form, eta. And this number will be bigger than -2. And the next part is this number actually will be detected by Floer theory. So if M admits a Liouville filling W such that the first chain class rationally is 0, then this number is detected by the minimum degree where you have non-vanishing positive S1 equivalent symplectic homology plus n-3, because this is supported in conic singular index. So n plus n-3 is this SFT degree. And I want to mention here that this condition that N admits a Liouville filling is just technical, because we want to talk about this S1 equivalent symplectic homology, but it doesn't depend on which filling you are using. And actually, if you want, you can replace this by linearized contact homology using any algebraic augmentation. And by a recent work by Julian Chadis, that this thing is also well defined. But in our situation, actually, we can always find the Liouville filling down. So you can use either one. Okay. And the thing here is because simplex homology is a particularly nice invariant, and we have many different ways to compute it. If you have a relation between the minimum discrepancy and simplex homology, you have alternate way to compute the minimum discrepancy. Then it go to the Fano index and prove the theorem. So before we dig into this theorem, let me first recall some basic concepts, because as I said that the minimum discrepancy from the definition, you can see all these AI is just rational numbers. So my ACFT number and the Collins-Cinder number has to be rational as well. So let me first recall what's the definition of a rational Collins-Cinder index. The situation at hand is we have the first chain class of the context structure 0. That means we can find the integer n such that if you take a direct sum of many copies of this context structure and take the determined bundle, then you can trivialize it because this first chain class is torsion. And then we can define the rational Collins-Cinder index as if you have a Reeb orbit and you have this root T as a linearized flow, which is essentially a path of symplectic matrix, and you take n copies of it. And after you choosing this trivialization, then this Collins-Cinder index is well defined, and then you take out this multiplicity by dividing by n, and that will give you a rational number. And this rational Collins-Cinder index is independent of the trivialization of this n. If this gamma is the homology class of this gamma is a torsion, which is also in the situation we consider. And in the case of if you have a simplex filling, we can view the first chain class of the filling, which might not be 0, as in the relative homology, because it's restricted to 0 on the boundary, and let U be a disk in W with boundary gamma. Then you have two ways to compute the Collins-Cinder index. One is using this rational one. One is using the induced trivialization from this disk. And their discrepancy is precisely measured by first chain class. This is just the classical change of Collins-Cinder index if you change the trivialization. Okay, and then in our notation we have, because the contact form we consider is typically of more spot form, so we need to use a lower semi-continuous extension of the Collins-Cinder index. This can be viewed as sort of the, since you are considered more spot case, this lower semi-continuous Collins-Cinder index is just the minimum Collins-Cinder index you get after you perturb your Morse spot family into the Morse case. And the LSFT, the lower SFT degree, is just the SFT degree using this lower semi-continuous Collins-Cinder index. So that explains all the terminology in the theorem. And next, let me explain why such thing should be true. So first of all, the theorem we prove is not new. There's an older result due to MacLean, which relate the minimum discrepancy and the Reeb dynamics on the boundary, which says the following. This is for general isolated Q gross times singularity. It says if MD is bigger than equal to 0, then twice MD is given by taking the infimum of the lower SFT degree, and then take the supremum for all the contact form. In our theorem, it says that you can forget about this supremum just using the sort of Sasaki contact form. It's already good enough. But in fact, in MacLean's proof, he also constructs some very nice contact form where you can achieve this infimum. Okay, and the reason why such thing should be true is this LSFT degree sort of measures the dimension of moduli space of holomorphic planes in the resolution that does not intersect exceptional divisor. Of course, we are not sure if such moduli space will exist, but there's always one such thing will typically exist in the resolution, which is a fiber disk. Okay, so you can, in fact, this fiber disk, which after you perturb this the more spot contact form into modes, the minimum one essentially corresponding to a holomorphic disk subject to a point constraint. So it's just after you fix a point, which will be sort of minimum of this Morse perturbation, you have exactly one holomorphic fiber there. The this modular space will have virtual dimension. This is cutout transversely, and this modular space will have virtual dimension 0. But this modular space, the virtual dimension, is computed using the conic singular index of this disk. So if you want to recover the conic singular index of this Reeb orbit, you have to compensate the error from the different framing or the error from the first chain class. And the difference is precisely this 2C1 of the resolution paired with this disk DI, which is precisely 2AI. So the end game is you want to show that such holomorphic curve will exist in different contact form. But this is morally why this minimum discrepancy and the this SFT degree, why should they be related? Okay, so go back to our situation. So we basically need to prove two things. First is the minimum discrepancy equals to the lowest SFT. And second is it's detected by a homology class in the symplectic homology, So so to compute the minimum discrepancy is by following method. First of all, if you consider this line bundle L inverse, it's sort of almost a resolution. If D is not an orbifold but a manifold, then it is a resolution. But in the general case, when D is orbifold, then this is still not a resolution, but it has only quotient singularities. And people has known for a long time how to write out formulas for the minimum discrepancy for quotient singularities, isolated or not. Locally, this L inverse will be modeled on this quotient, where the first factor C is the line bundle direction, and the Cn minus 1 is the base direction. And the minimum discrepancy here will be given by this formula, where R is this negative KD is RL, is this you can call it a Fano index. And this minimum is taken from, you take a singularity in this line bundle, total space of line bundle, and you take an element in the kind of isotropic group. If it acts by this action, then you take out this number. That's the minimum discrepancy. And then we can compute the minimum we can compute the minimum LSFT as well. The way to compute it is first you realize that this Fano index is actually a Maslov index, because our contact form is quasi-regular, so it's coming from S1 action. And I will call orbit a principal orbit if it's sort of over generic point over D. So that's a point where this action is free. And so in particular, this S1 action will give us kind of a loop of symplectic matrix instead of a path, because it's close up. And this 2R is precisely the Maslov index of this loop of symplectic matrix coming from the linearized flow around a principal orbit. Of course, R here could be rational, so I'm also using the same definition of the rational conic singular index to define same rational Maslov index. So this Maslov index will tell me the minimum, the correct minimum lower semi. So it will tell us the lower SFT of a principal orbit. And then we can using the framing coming from this local model to understand all the Reeb orbit. But the problem is, using this local model, maybe you are computing the wrong conic singular index because your framing could be different from the framing you are using globally. But inside this local model, you can always find a principal orbit, and you can compute using this local model framing what is the lower SFT for the principal orbit. But since you already know the answer for the correct principal orbit lower SFT, you can compare and understand what's the difference in framing, and then you can correct all the computation to figure out the lower SFT for all the Reeb orbits. And when you put them together, you find the formula is on the nose exactly the same. And this proves the first equality. To prove the second equality, we need to recall briefly the Sinclair homology and its variance. So basically, we were using these basic properties of Sinclair homology, the positive Sinclair homology, and the S1 equivalent positive Sinclair homology. They have all these structures, exact sequences, and in particular, photographic transfer map preserving all the structures. I'm sure this is should be familiar to most of the audience. And in this talk, the only thing I care about is the Sinclair homology of Cn, which is 0. And then using the tautological exact sequence here, and also using the Giesen exact sequence here, you just compute the Sinclair homology of Cn positive Sinclair homology. S1 equivalent is given by this, supported from degree n+1, and then n+3, and so on. Okay. So go back to our situation. So we need to compute the Sinclair homology of our Sasaki manifold. But since it's coming from S1 action, it's actually a more spot situation. And just think of the rational ellipsoid. So you can have if you have round sphere, then everything have the same periodic periods. But in the general case, you can have some point, some orbit have longer period, and some other simple orbit have shorter period. But in general, you just have this more spot exact sequence just by figuring out what are the Reeb orbits are. And in particular, the first page is just computing the homology of the Morse spot family. And the Morse spot family here we're corresponding to the part of a Reeb orbit, which if I say the principal the period of a principal orbit is 1, then what I mean by this GKL is corresponding to the Reeb orbit with period is K quotient by G and plus L. So it's sort of this orbit which with coming from with isotropic group is order G, but you go around K times and followed by L times the principal orbit. And these are all the Reeb orbit family. So you have this you have this spectral sequence, and this is a kind of a schematic picture of the exact sequence. So this block will corresponding to a homology of some family DGI. And the P plus Q is a rational grading. And the minimum one here is a sort of a corresponding lower conic singular index of this family. But in our situation, because we know that the conic singular index is always defined over Z over 2. So we also have a Z over 2 grading. And this is indicated by the color here, by red and blue. And since all my Reeb flow is coming from this algebraic consideration, you can verify the Reeb flow, the return map, the conic singular index of this leading term is always of the same parity. Okay, and then when you look at this spectral sequence, how you can see you want to argue something in this minimum, something in this like minimum. You're trying to use this slope -1 thing to scan this spectral sequence, and you want to see some dot on this line will survive. But the claim is you find on this line, you always find this line, and you find the highest term. The highest term here will always survive in the spectral sequence, because if it does not survive, also the highest corresponding to the highest red point. So maybe I should use highest red point. Because if it does not survive, that means there must be some blue point go to kill it, but your differential slope is always like vertical or go into the sort of this direction. So that means if that happens, you will have another red dot here or even further. So contradict your choice. So that's just a very simple proof that the minimum element here will survive in the homology. Okay. So now we finished the proof of our main technical theorem. Let's see how we assemble this back into our geometric question, which is compactification of Tian. So the first, we start with the situation is you have this is your Cn, and you have a compactification, and here is your D. And then you sort of have a kind of boundary of neighborhood, which is this N. And you can show that this N is a strongly pseudo-convex. It's a Levy-convex hypersurface. So in particular, by a result due to Homaunder, says the domain bounded by it, this W, is the Liouville domain. And you can compute the homology of this N, D, and everything. So homological computation implies that the homology, at least rationally, this D is the same thing as Pn minus 1. And homology is the same as sphere. So everything is standard. The homology is the same as the same as the standard one. Okay, and then the AC condition. So just having this N is strongly pseudo-convex is not good enough. The AC condition actually tells you that there's a Liouville coboson V from N to S to minus 1. The AC condition basically means that the R on this cone, this function, is a PSH, Claris subharmonic, strictly Claris subharmonic function. And you also have on Cn, you have this Euclidean R square. Maybe use R square. This is also PSH. You can interpolate between this PSH and to build a coboson from N, which is the level set of this R, to a level set of this R, which is sphere. Yeah. So this AC condition is needed here to build this coboson. And then there's a result due to Seidel-Smith, which implies that the simpler homology, when you gluing this W with V. So W is a domain bounded by the link of N, and the V is the coboson you get from interpolating these Claris subharmonic functions, because this is a filling of, it's a Liouville filling of the standard contact sphere. And their theorem says that any simpler filling, exact filling of the standard sphere will have the simpler homology 0. So the fertile functoriality will imply that the simpler homology of this W is 0. And then because we from topological computation, you know the homology of W is just a ball. The homology is the same as a ball. Then using the tautological and the Giesen law exact sequence, you can compute it that this simpler homology, positive S1 equivalent simpler homology of this W is the same as the corresponding invariant of Cn. And in particular, it implies that the minimum description of the singularity is n-1. So I'm thinking of, so this is our D, and this is our N. So this is sort of, M is a concave boundary of this neighborhood of D, and this, the normal boundary here is L. But I can also view this as a boundary of L inverse. So like view it as a link of singularity because my divisor, this D is smooth. Yeah, so we know that this minimum discrepancy of the singularity corresponding to this D and L is a -1. And that implies from our basic example where when if D is smooth, then we already showed that the basic example, if the minimum discrepancy is exactly the Fano index -1. And you can compute that this -1, so the Fano index has to be n. Then by the Kobayashi-Ochai characterization of Pn -1, we know the index, we know the D is just Pn -1. Okay, so in short, this is just because you know this first string class is in the grading of symplectic homology, and you know how to compute symplectic homology, so you know the first string class, and hence you know the Fano index. That's, yeah. And in the general case, when D is a orbifold, we assume that this Shorokhanov conjecture is true. So in particular, the metric cone at infinity, which will have this M as our link, will be a smooth Cn. So the tangent cone at infinity is Cn. And also, because it's tangent cone of a Calabi-Yau metric, it's also Calabi-Yau. And moreover, it will have a linear torus action, which is generated by this Reeb flow. And there's a classification of this action with a kind of a fixed point in the center. It's always linear like this. But so far, we haven't using the Calabi-Yau metric in a serious way. So because this tangent cone at infinity is Calabi-Yau, that means the Sasaki link is Einstein, and it's Einstein with a constant, with a fixed Einstein constant. This is true for all Sasaki manifold. And being Einstein means that it will have some volume maximizing property, and that will imply that the weight can be this weight can be used to express the volume, normalized volume of the Sasaki manifold. And you can figure out that to have the Einstein metric on the Sasaki link, you must have the weight is the same, and then you can from there argue that the tangent cone at infinity must be flat. And finally, is a result due to Anderson, which says basically, if you have the which says, I think it says that if two things are close to each other in the Gromov-Hausdorff sense and with bound on rich curvature, then under some assumption, you can argue that the metric has to be flat. And in this case, it's precisely enough to using his result to conclude that the original Calabi-Yau metric is flat. And that's all I want to talk about here. Thank you.
Thanks. Any questions?
Oh yeah, so the symplectic homology or positive symplectic homology computations for like links of singularity is like, it seems like quite similar to this Evans-Lakili work. Are the computations like contained in this work, or is there some other clear relation?
So my computation here is sort of fairly simple. It's basically because it's coming from the compactification of Cn, and you basically want to show the link is standard contact sphere, but you cannot argue that. But it's covalent to standard contact sphere, so you can still compute first the symplectic homology of any filling has to vanishing, and then using these properties compute. So I think what I have here is much simpler than any serious computation. So it's just some argument to show that the situation is really the same as the standard one you have in mind.
But it seems like the sort of the spectral sequence argument is applicable to like do lots of more computations.
Yes. Yes, but to prove the leading term with non-vanishing, only essentially I think use the action filtration plus the C2 grading. I think it's already enough to know the leading term will not vanish. Of course, in our case, we are like the Fano cone singularity will tell you the Fano index is R is bigger than 0. That essentially means that all this cone singular index is growing. So you can always pick out this minimum one.
Okay, thanks.
Thank you.
All right. Can you say something about the non-Kähler case?
I can't because if it's non-Kähler, I don't even know the link is contact.
Is it?
Yeah. So it's really the real price of this thing is you want to drop the Kähler assumption, but a big problem, for example, if you drop the Kähler assumption, you don't even know the homology of D is non-trivial. Yeah, but if it's Kähler, then it's automatic. Yeah, so it's definitely also beyond symplectic geometry, I guess. But also in this Shortcut conjecture, it actually has two parts. One is the minimum description has an upper bound. The other is where it achieves the upper bound, then it has to be smooth. We now know how to prove that for this Fano cone singularity, the upper bound is indeed n-1. But that's not good enough for us to prove this AC Calabi-Yau is it must be flat conjecture for all the dimensions, because we still need to recognize its smooth point. It's more or less like recognize a weighted projective space, how to characterize it. We don't have an analog of Kobayashi-Ochai for weighted projective space.
Okay, so if there are no further questions, thank you again.